Welcome back, everyone. So before we get going, I want to make sure that I get through a little bit of housekeeping. So as far as housekeeping goes, just as a reminder, we do have our first chapter summary due tomorrow. That's the Anatomy and Physiology chapter summary. It's due tomorrow. I think I'm up to date on grading for those people that have already turned them in. And I see people have already started to turn in the pathophysiology summaries. So I will get to those as well. There will be some homework that will open up today as well as it pertains to the topics we've been covering the last couple of days. And I'll remind you all of that before we conclude lecture today. But I just wanted to give you all a heads up. So you'll have some assignments that you'll be working on today and then through the weekend as well. Okay, aside from that, are there any questions about anything we've gone over thus far? I know we've gone over quite a bit of information in a short amount of time, so just want to make sure that there aren't any questions. Okay, excellent. All right, so what I'm going to do is I'm going to send everyone a little poll. This is just a review question. It's not going to be a Padlet, but rather it is going to be a poll that will go through Zoom here. And it's just a question, and I'll give you all a few minutes to look at it and answer it, and then we'll go ahead and review after everyone's answered. So let me go ahead and do that right now. It's a multiple choice question with a little picture. So I'm going to go ahead and launch that. All right, there it goes. You all should have that. So I'll give you all a couple minutes to answer that, and then we'll go over it together. All right, we'll go ahead and end the poll there. And let's go ahead and take a look. So it's fairly split between the three answers. That's interesting. So let me pull this up for you all real quick. And I will go over the answer to this. So this is kind of a fundamental answer because it really is asking if you're able to identify an acid. So these are the three molecules that I had a diagram of. This is molecule A. Let's see, you all should be able to see that. All right, so that's molecule A. This is molecule B. And then this is molecule C here. All right, so those are our three options. And so A, B, C, and it looks like a slight, just under half the class answered C. And then it was split more or less evenly between A and B. So let's talk about this. So first of all, let me ask you all, what do you think? Which one of these is going to be an acid?
So I go with C because of the hydroxyl group.
Yeah, I would
which
say
means
C
it
too.
donated an H.
Okay, you're on the right track. So hydroxyl groups by themselves are not always acidic. It is this entire functional group here, this configuration that makes it acidic. But you're right that this entire functional group, does anyone know what the name of this functional group is right here? It's the most common functional group that we see in organic acids.
Acetate.
No.
Is it a carboxyl?
Yeah, this is a carboxyl group. So you have a carbon double covalently bound to an oxygen up here, and then you have the carbon bound to a hydroxyl group here. And this configuration is a situation that allows this hydrogen to fairly easily pop off as a proton. And then you're left with the anion or the conjugate base. So this is actually a molecule of acetic acid. And of course, after it donates its hydrogen ion, you would be left with citrate or acetate, excuse me. B is a molecule of acetone. And we're looking at a ketone group right here with this carbon in the middle, double bonded to an oxygen. And then you have these two functional groups coming off, and it has to be something other than a hydroxyl group. And then this here, so B, this is not particularly acidic at all. And then A over here is NH3. We talked about that yesterday and last week. That is ammonia. You've got a pair of electrons on top of the nitrogen, and then it's covalently bound to 3 hydrogens. And nitrogen, if you remember on the periodic table of elements, nitrogen's kind of over there on the right. So it's fairly electronegative, not on the order of, say, something like fluorine or chlorine, but it is going to hold on to the electrons. And so ammonia doesn't particularly like to give up these hydrogens. And so this is not particularly acidic. In fact, oftentimes these ammonia-based molecules are referred to as amines, are often very basic in nature as opposed to acidic. So the correct answer is C here, because as some of you had mentioned, you've got this carboxylic acid or this carboxyl group here that makes it to where this hydrogen on that hydroxyl group is more likely to pop off when dissolved in water. Excellent. So are there any questions over that?
Can you explain B again? I'm sorry. I
B?
chose C, but yeah, can you explain C?
B you
B.
said?
Yes, yes, sir.
Sure. Let me go back in here. So B was this right here. So this right here in the middle, where you have a CORR, this is what's known as a ketone. That's a ketone functional group. And so you can see the ketone functional group here with the CO, and then this is one of the R's. R just means something else, some other, carbon, hydrogen, whatever. And this is something other than a hydroxyl. So that makes this a ketone, and the specific ketone that this molecule is a molecule of acetone. And you can see that's very different from this here. Molecule C. It has a similar structure, but you see that this methyl group here has been replaced with this hydroxyl group here. And this entire group, the COOH, is a carboxyl group. and that H is able to pop off as a hydrogen ion. So that's what differentiates, say, a ketone from a carboxylic acid. So this is acetone here, and then this is acetic acid over here. Just one functional group, like we talked about last week, just adding or taking away one functional group can profoundly change the molecule and how it interacts. All right, any other questions? Excuse me. All right, I'm just going to check and chat, make sure I don't miss anybody. All right, excellent. Well, let's move on then. So now what I want to do is I want to move on and I want to talk about acid-base imbalances. Well, we spent a lot of time building up the foundation. Let's get into acid-base imbalance. So just as a review, when it comes to conceptualizing acid-base, we're really going to look at three major values. We're going to look at the pH. And what is a normal pH?
7.4.
7.4.
7.4. All right. So 7.4 is perfectly normal. And then 7.35 to 7.39 is what we say acid normal. And then anything less than 7.35, right? So anything less than 7.35 is full on acid. And then the same thing here, 7.41 to 7.45 is what we call base normal. And then anything greater than 7.45 is full on base, or what we call alkalosis. All right. So that is a concept of pH. The next is PaCO2. We said the normal value is 35 to 45 millimeters of mercury. And remember, Rome, CO2 and pH are opposite of one another. So a pH of less than 35 will, or a CO2, excuse me, of less than 35 will tend to make the patient more alkalotic. And a pH of or CO2 greater than 45 will tend to make the patient more acidic. And remember that this is the respiratory component of the patient's acid-base status. And then the bicarbonate, and the bicarbonate is 22 to 26 milliequivalents per liter. And going with Rome, respiratory opposite, metabolic equal. So the bicarbonate moves in the same direction. So a bicarbonate of less than same direction as pH. A low bicarbonate is going to correspond to a low pH. And so bicarb less than 22 is indicative of acidosis. And a bicarbonate of greater than 26 is indicative of alkalosis. And remember, the bicarbonate is looking at the metabolic component of acid-base balance. So it's the interplay of these three concepts that we are going to be looking at in order to determine acid-base status. All right, so when we look at acid balance, we have normal, and to say that somebody has normal acid base, all right, normal acid base, the pH has to be in the normal range. All right, so 7.35 to 7.45. Now, that's not the only thing. because if the pH is 7.36, they may have normal acid base or they may have some problem. But that is one criteria that needs to be met. The second criteria that needs to be met is that the PaCO2 must be in the normal range. And the third criteria that has to be met is the bicarbonate has to be in the normal range. All right. So those are the three criteria. And what are abnormal? What are some abnormal conditions? Well, what's generalized? So the general abnormal condition really going to fall into a couple of different categories. We can have, on one end, we can have an alkalosis. On the other end, we can have an acidosis. And occasionally, we can get what's called a mixed deficit. You know what? I'm going to get rid of that. No, let's not do that. Let's see. I want to simplify it even more. You've got normal, you've got acidosis, and you've got alkalosis. All right. We're going to keep it at that. Now, when it comes to acidosis, there are three major ways that you get to an acidosis. You can develop an acidosis through failure of the respiratory system, and that is referred to as a respiratory acidosis. And so with a respiratory acidosis, you're going to have an elevated PaCO2. You have an elevated PaCO2, and you will have a pH that is less than 7.4. All right. You can also have a metabolic acidosis. All right. And a metabolic acidosis will occur when you have a pH that's less than 7.4 and a bicarbonate that is low. All right. So a CO2 of greater than 45 and a bicarb of less than 22. All right. And then the other type of acidosis that you can get is something called a mixed acidosis. And this is a combination of a low HCO3 and a high PaCO2 with a pH that is less than 7.4. All right. So you've got respiratory acidosis, metabolic acidosis, and mixed acidosis. Guess what? The same thing applies over here with alkalosis. All right. You can have a respiratory alkalosis, and this is going to be a pH of greater than 7.4, or that's a requirement. It has to be greater than 7.4. And with a respiratory alkalosis, you're going to have a low PaCO2. So you're going to have a CO2 that is less than 35. And then you can have a metabolic alkalosis where the bicarb is elevated. So the bicarbonate is going to be greater than 26. And then finally, you can have a mixed, although this is fairly rare, where you would have a low CO2 and a high bicarbonate. All right. Those are the major deficits that we can run into. Is everybody okay with that so far?
Yes.
All right. Now, the final thing that we'll need to do is once we identify a problem. So step one is can we identify a problem, right? Step two is what's causing a problem? Is it a respiratory, metabolic, or mixed? And then step three, and this tends to be the hardest because it's not intuitive for some people. Step three is you need to identify compensation. For example, if the respiratory system fails and carbon dioxide increases and pH decreases, right? We would say the patient has a respiratory acidosis. So what you need to do is once you identify the problem, acidosis, the cause, respiratory, then what you need to do is you need to ask yourself, is the body attempting to compensate, right? So what you do, let me just give you some values here. So let's say that we look and our patient has a pH of 7.3, a PA CO2 of 57, and a bicarbonate of 24. All right. So step one, look at the pH and ask yourself, is the pH normal? So perfectly normal be 7.4. Is it acid normal? Is it base normal? Or is it full on acid or full on base? All right. So remember, normal 7.4, acid normal is 7.35 to 7.39. Base normal is 7.41 to 7.45. Full on acid would be less than 7.35 and full on base would be greater than 7.45. All right. So let's look at the pH. Step one. Is the pH acid, base, normal, acid normal, base normal, or perfectly normal?
Acid.
Acid.
Acid base.
Yeah, acidic.
I'm going to put acid, right? And I'm just going to write an A there. So that's full on acid, right? No wiggle room. And then I'm going to drop down. So now that I've identified the problem, this is fairly easy. There's an acidosis. And then I need to ask myself, okay, where's it coming from? Right? So then step two, I find out where the problem's coming from. So I move down, I look at the CO2 and I ask, is the CO2 acid or base? And so a CO2, if we remember, a CO2 of over 55 is acid and 45. Over 45 is acid and less than 35 is base. Right. So is the CO2 acid, base, or normal?
Acid.
Acid, right? And then I move down and I look at the bicarb. And remember, a bicarb of greater than about 26 is going to be base. Less than 22 is going to be acid, right? Is everybody okay with that? So I look at the bicarb and I ask myself, is that acid, base, or normal?
Normal.
It says normal.
Normal.
So it is normal. I'm going to put an in there. Now I have all the information to make the diagnosis, so to speak, or to interpret the ABG. So the way that we write out our interpretation is I write out the problem first. So what is the problem? Is it an acidosis, an alkalosis, or is it normal?
Acidosis.
Acidosis.
Okay, so everyone agrees that we've got an acidosis here. Good.
Yes.
And then the next step is I identify the cause. So now that I know there's a problem, what's causing it? Is it caused by the respiratory or the metabolic system?
Respiratory.
Good. So I'm just going to rewrite it here. So I'm going to say that we have a respiratory acidosis. And then the final step is I ask, is the body trying to compensate? So once I've identified the cause, I connect the dots. I move down to the third component. So if this is a respiratory acidosis, I'm going to look at the metabolic, right? And I'm going to ask myself, is the metabolic component attempting to compensate? So if there was compensation here, what would the bicarbonate be doing?
Would it be elevated?
The bicarb would elevate, right? Now, what do we see here? Is the bicarbonate elevated?
Negative. It's in the
No.
sweet spot.
Negative. And in fact, whenever I see the third value, whatever it is, if it is normal, that tells me that there is no compensation there. So the problem is a respiratory acidosis and the body is not compensating. And so we would call that an uncompensated respiratory acidosis. So most ABGs are going to have three names, a first name, a middle name, and a last, right? So now what I'm going to do is I'm just going to work through some more examples with you all. So let's do this. Let's do another example, and I'm going to keep the numbers really similar.
Chris, I have a quick question.
Yes.
So whenever there's compensation, does it always depend on the bicarb?
If you're dealing with a respiratory acidosis, yes. But as we're going to find out, we're going to work through some examples and see that it doesn't always depend on the bicarb.
Gotcha.
But for now, it will, just because we're looking at the respiratory. But I think it'll become a little more obvious as we work through a few more. So let me do this here. All right. All right, so I've got another ABG here. So let's look at the pH first. Is it pH acid, base, normal, acid normal, or base normal?
Acid.
It's full on acid. Okay, so we have an acidosis. Well, let's figure out what's causing it. So let's look at the CO2. Is it acid, base, or normal?
Acid.
Acid, good. And then let's look at the bicarbonate. Is it acid, base, or normal?
Base.
It's base. Okay, so what's the problem?
Compensated respiratory acidosis.
No. Don't get ahead of ourselves. So what's the problem?
Acidosis.
Okay, so there's an acidosis. And what's causing the acidosis?
Respiratory.
Good. So I'm going to just connect the dots there. So we have a respiratory acidosis. Now the last question I need to ask myself is there compensation?
Yes, there is.
Yes, there is, but we're not quite done yet because there are different types of compensation.
Would it be partial?
Yeah, so let's so everyone agrees that the metabolic system is compensating, right?
Yes.
It's trying to, it's becoming more alkalotic to try to offset the respiratory acidosis. But the question you need to ask is So is there compensation? We all agree yes, but is it getting the job done? And if it is getting the job done, what would happen is the pH would be in the acid normal range. All right, so if you have a high CO2 with a pH that is between 7.35 and 7.39, because it is shifted into the normal range, we would say that this is a fully compensated. However, if the pH is less than 7.35, then it is what we call partially compensated. All right. So when we look at this patient's pH, it's 7.3. So is that in the acid normal range, or is that less than the acid normal range? What do you all think?
Less.
It's less. So I think someone mentioned earlier that would make this partially compensated. It is trying to compensate, but it can't, it has not been able to shift the pH into the normal range. Not normal, but normal range. So we would call this a partially compensated respiratory acidosis. So let me give you all another example to contrast with. Oops. So let's say we have this patient here. All right, so let's look at the pH. Is that acid, base, normal, acid, normal, base, normal?
Acid normal.
So this is an acid normal pH. Now, what does that mean? Well, that means one of two things. That means we could have a normal ABG if the CO2 and bicarb are normal. If the CO2 and bicarb are normal, then we would have a normal ABG, or it means that there is a compensated acidosis. It has to be one of those two things. So what we're going to do is we're going to look and we're going to say, hey, is there some underlying problem? So let's look at the CO2. Acid, base, or normal?
Acid.
Acid. So we agree that CO2 is acid. Let's look at the carbon. Acid, base, or normal?
Base.
Yes.
Base. Good. So we do have a problem, even though the pH is in the normal range. And so you could, hopefully you can understand why I've been so aggressive about saying no. 7.35 to 7.45 is not necessarily normal, because here we have a situation where there is an acidosis with the pH being in the normal range. It's in the acid normal range. So there is a respiratory acidosis. Because that CO2 is elevated. Is there compensation? Yes or no?
Yes.
It's a yes.
Yes. The bicarbonate is moving to try to compensate. And then the next question is so 7.35 to 7.39 or under 7.35. So is the bicarbonate, is the metabolic component getting it done?
Yes.
Yeah,
Yes.
it has been able to shift the pH into the acid normal range. So we would, again, we would call this a fully compensated. So I would just write compensated or fully compensated respiratory acidosis. So I wanted to give you 3 examples of a respiratory acidosis. One where there's no compensation at all, one where there's partial compensation and one where there's full compensation. And hopefully you can make those connections there. We're going to work through several more examples of anomalies though. But
Hey,
if
Chris,
everybody- yes, go
let
ahead.
me ask a question. We're still at 57 on the partial artery CO2.
Yes.
Does that mean, because I mean, we're still at 57, we're not down to 45. Are we, I know you called it fully, but do we have a specific number that we have to get to say, okay, now we're fully, because I know the basic is still working. We're still,
Yeah. So yeah, so what makes this a fully compensated acidosis is the pH. So the pH is if there is an acidosis. So if you identify a high CO2 or a low bicarbonate, that's what makes an acidosis. Then you need to ask what kind of acidosis, and if the pH is between 7.35 and 7.39. So if the pH is in the acid normal, that's what we call the acid normal range, and then 7.4 is perfectly normal. And then 7.41 to 7.45 is what we call base normal. All right. And then anything out less than acid normal is just full on acid. So I'll use a different color here. So when we look at this ABG up here, the pH is full on acid, right?
yes, sir.
And the bicarbonate is completely normal. So the metabolic system has not even tried to compensate. So that's fairly straightforward. It's uncompensated. But if we look at this one, the pH is still the same. It's still full on acid, but the bicarb has moved. It's trying to compensate, but it hasn't even been able to get the pH back into the acid normal range. And so it's failing to compensate. So that's what we call a partially compensated. It's trying to, but it's just not getting the job done. And then this one here, the pH is 7.37, which puts it in the acid normal range. So you still have the respiratory acidosis, but the metabolic component has been able to at least shift the pH back into the acid normal range. And that's what makes it a compensated or fully compensated respiratory acidosis in this case. Does that kind of make sense?
Yes, sir, it does. I was just
Cool.
wondering about the partial
Yeah.
carbon dioxide. Thank you.
Yeah, no worries. No worries. And I tried to keep the values the same, so it made it a little easier to compare each ABG. Right. Let's just work through a few more examples of ABGs, and that'll take us to our first break here fairly quickly. So let's see here. Make sure that's good. All right. So let's do this. Okay. So let's look at this ABG here. So pH, acid, base, normal, acid normal, or base normal? What do you all think?
Acid.
It's,
This is a full-on acid. Good. All right. CO2, acid, base, or normal?
normal.
Normal.
Normal. So I'm going to put a big in there. And then let's look at the bicarbonate, acid, base, or normal?
Acid.
Acid.
Acid. Good. It's a low bicarbonate. So in this instance, my problem is an acidosis that's caused not by the respiratory system, but rather the metabolic. So this is what we call a metabolic
Acid.
Good. Acidosis. And let me ask a question. Is there any compensation going on here?
No, it's uncompensated.
No. So in a metabolic acidosis, we look to the respiratory for compensation. With a respiratory acidosis, we look to the metabolic for compensation. So in this case, the CO2 is normal. And remember, N normal means no compensation. So this is an uncompensated metabolic acidosis. All right, well, let's look at another example then. Do this.
So just to rephrase that, so respiratory acidosis, if there's any compensation, you will notice it in the bicarb. And if there's
Yes.
compensation in the bicarb, you'll notice it in the PaCO2.
I think you're on the right track. So with a respiratory acidosis, you look to the bicarb for compensation. And with a metabolic acidosis, you would look to the CO2 for compensation.
Gotcha.
Cool. So let's get another example, 7 point. Again, I'll try to keep this as simple as I can to help with the learning. So we're going to go here. All right. So pH, acid, base, normal, acid, normal, base, normal. What do you all think?
Acid.
All right. So this is full on acid. CO2, acid, base, or normal?
Base.
Base.
Base. Good. And then bicarbonate, acid, base, or normal?
Acid.
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 Acid. All right. So the primary problem is an acidosis that's being caused by the metabolic. So we would call this a metabolic acidosis. Everyone agree there?
Yep.
Okay. So then the final question is there compensation? And so we will look to the respiratory component. Is there compensation here?
Partial.
Yeah. So the patient is blowing off CO2, right? They're blowing off CO2 to try to compensate, but is it getting the job done?
No.
No.
Negative.
It's because the pH is still outside of the acid normal range. And so it's trying, but it's just not getting the job done. So this is a partially compensated metabolic acidosis. And then the next thing is, let's just do this here. All right. So let's look at this ABG. So pH, acid, base, normal, acid, normal, base, normal.
Acid normal.
So this is acid normal. So there may be a problem, there may not. Let's see. CO2, acid, base, or normal?
Base.
Base.
CO2 is base. Good. And then bicarbonate, acid, base, or normal?
Acid.
Acid.
This is acid. So we do have an acidosis. We have a acidosis that's caused by the metabolic. So there is a metabolic acidosis here. And then the last question is there compensation? Is the respiratory system compensating?
Yes.
Yes. Is it getting the job done?
Yes.
Yes.
Yes, because the pH is in that 7.35 to 7.39 range. And so this would be a fully compensated metabolic acidosis. So you can see 3 more examples. And let's just do this here real quick as well. So let's say that I've got a pH of
39 normal. CO2. 38.
All right. So pH, acid, base, normal, acid, normal, base, normal.
Acid
Acid
normal.
normal.
All right. So it is acid normal. So there may or may not be a problem. Let's see. CO2, acid, base, or normal?
Normal.
Normal. Bicarbonate, acid, base, or normal?
Normal.
Normal. So if you have an acid normal and everything else is normal, you can call this a normal acid base. Right. But everything else has to be normal. So you could be acid normal or you could be base normal. And as long as the CO2 and bicarb are normal, it is a normal ABG. If they're not, then there's a problem. And let me give you another example before we take a break. Let's do this here. Okay. So pH, acid, base, normal, base, normal.
Acid.
Acid.
Full on acid. CO2, acid, base, or normal?
Acid.
Acid, good. Bicarbonate, acid, base, or normal?
Acid.
Acid.
Acid. So acid, acid, acid. So this is an example of what?
Mixed.
Yeah, this is a mixed acidosis. So this is failure of both the respiratory and metabolic system. So this is a very sick individual indeed. All right. Well, we are almost at 9:30, if you can believe it. So are there any questions, or you all want to take a quick break and then we'll come back and I'm just going to keep working through more examples. Well, excellent. Let's take a break. What is it? 9:25. So I'll see you all back at 9:40. Welcome back. Welcome back, everyone. All right. Hopefully you enjoyed the break. So before we get going, are there any questions?
I gotta just to clarify some things. It might be rhetorical, but I got something.
What you got?
Everything like in your PCO2, everything below your 35 is a basic, and everything above 45 is acidic or acid.
Yes. Yes.
Okay. And then same thing with your bicarb. Anything below 22, basic, and everything above 26,
No, no.
acidic. No.
No, bicarbonate is, it moves in the same direction as, so remember Rome?
Hmm.
So respiratory opposite. So a CO2 under 35 is base, and a CO2 over 45 is acid. So that means that a low CO2 is going to tend to increase the pH. And a high CO2 is going to decrease the pH. And that's opposite with the bicarbonate, right? So
Are you trying to share your
a-
screen because we can't see anything?
Oh, you can't see it?
No, sir.
Let's see here.
So when you're bicarb, it would be okay. So I just have it backwards. Okay.
Yeah, you just had it backwards. So the bicarbonate moves in this, it will move in the same direction as the pH. So
That's the
let me-
pH.
there we go.
Okay.
So a
Okay.
high bicarb will increase the pH, and a low bicarb will decrease the pH. So that's metabolic equal. So the pH and the bicarb will move in the same direction, whereas the CO2 and the pH will move in opposite directions.
Okay, yeah, I just had it backwards.
Cool, not a problem. All right, well, let's move on. Let's just work through some more examples. All right. All right, so let's take a look at this ABG here. So pH, acid, base, normal, acid, normal, base, normal. What do y'all think?
Base.
So this is full on base. Okay, so let's find out what's causing it. CO2, acid, base, or normal?
Base.
Base.
All right, low CO2. All right, basic. And then bicarbonate, acid, base, or normal?
Normal.
Normal. Good. So what's the problem here? What's the primary problem, first of all?
Alkalosis.
Respiratory.
No, it's metabolic.
So
No,
we've got
shit,
an
sorry.
So we got a respiratory alkalosis. Good. So a respiratory alkalosis. And is there compensation? So let's look to the metabolic component and see if there's any compensation. Do you all see any compensation there?
No.
Negative.
No. Negative. So this would be an uncompensated respiratory acidosis. All right. Well, let's look at another example here. Right. So pH, acid, base, normal, acid, normal, base, normal.
So would it be partial respiratory alkalosis?
Well, yeah. I just want to work through every step, but we'll get there. You may very well be right though. So pH, first of all, acid, base, normal, acid, normal, base, normal.
So base.
All right, good. Everyone agree that that's basic? All
Yes,
right, CO2, acid, base, or normal?
Normal. No, that's a basic.
That's basic, good. It's less than 35, good. And then bicarbonate, acid, base, or normal?
Acid.
Acid.
Acid, all right. So same thing, we have an alkalosis that's caused by the respiratory system. So this is a respiratory alkalosis. And is there compensation?
Negative, because pH is still not in the normal range.
So that is not compensation.
Partial.
Remember, compensation is look at the other component and ask, is it trying to correct the problem? So is the metabolic component, the bicarbonate, trying to correct the respiratory alkalosis?
Negative.
It is.
Is everybody okay with yes, it is?
Yes.
Yeah.
Okay, because the problem is an alkalosis caused by the respiratory system. And if you look at the metabolic system, it is becoming acidotic, right? To try to offset the alkalosis. It's just not getting the job done, right? So is there compensation, yes or no?
Yes.
Yes, but it's not fully compensated. So again, for it to be fully compensated, the pH would need to be in the 7.41 to 7.45, right? For a fully compensated metabolic alkalosis or respiratory alkalosis, right? We would need to see a pH in that range. But in this case, the pH is greater than 7.45, right, out here. So it's not fully compensated, but rather it is partially compensated. Respiratory alkalosis. So you can see a difference. The pH is abnormal up here, but the bicarb has not changed at all. So that's no compensation. The pH is still the same down here, but the metabolic system is trying to get the pH to change. It just hasn't been able to shift it down into the alkaline normal or the base normal range. So let's do this here. Let me give you a third example. There we go. All right, and let's just do this step by step. We'll do a systematic approach. pH, acid, base, normal, acid, normal, base, normal.
Base
It's
normal.
normal.
We go base.
So yeah, this is the base normal. So there may or may not be a problem. Let's see. CO2, respiratory, acid, base, normal.
Go acid.
Base.
Oh no, base.
Base.
Base, good. Yeah, low, good. So it is a low CO2 and a high pH. So that tells us that this is a respiratory alkalosis that we're dealing with. And let's move on and ask ourselves, is there compensation?
Yes.
Well, the bicarbonate is acid, right? It is compensating, and has it shifted the pH into the base normal range?
Yes. So you would have a full.
Yeah, so this would be a fully compensated respiratory alkalosis. All right, let's work through a few more examples. So pH, acid, base, normal, acid, normal, base, normal.
Base.
Good, full on base. CO2, acid, base, or normal?
Normal.
Normal. And then bicarbonate, acid, base, or normal?
Base.
Base.
Base. All right. So this would be an example of a metabolic alkalosis. And is there compensation?
No.
No. So if it's a metabolic problem, we look to the respiratory system for compensation. And this would be an uncompensated metabolic alkalosis. Good. All right. So now let's take a look at the following.
So I got a quick question, Chris.
Yes.
So to decipher whether it's a respiratory or metabolic alkalosis, it would be the basic in the bicarb.
Right. So remember, but yeah, bicarbonate is always going to be the metabolic component of acid base. And then the CO2 is the respiratory component of acid base. Yeah. And if you want, we can even just write that right here, just as a reminder. So as we look down on the second ABG, start with the pH and we ask, is it acid, is it base, is it normal, acid normal, or base normal?
Base.
Okay, it's full on base. So we know that there's an alkalosis of some sort. And now we just need to ask, well, what's causing it? So let's move on. CO2, acid, base, or normal?
Acid. Oh,
Acid. Well,
Yeah.
It's acid.
CO2 is acid, so that can't
Yeah.
be the cause of the alkalosis. So let's move on to the metabolic and ask ourselves, is it acid, base, or normal?
It's acid.
So it's 28. The bicarb's 28.
Base.
base.
That's base, right?
No space. Oh,
Remember-
shoot.
Yeah, remember Rome. Yeah, so it's greater than 26. So there's an alkalosis, and the B's line up. You see why I'm drawing B's there and drawing those arrows, because I'm lining things up to make the diagnosis. So this would be a metabolic alkalosis. And is there compensation?
Yes.
Yes. So the
Partial.
lungs are trying to make it more acidic, but yeah, someone mentioned it hasn't shifted the pH into the normal range. So this would be a partially compensated metabolic alkalosis. Now let's take a look at another example here. All right. So let's look at the pH. Acid, base, normal, acid, normal, or base, normal.
Base normal.
Base normal. So there may or may not be a problem. Well, let's move on down. Let's look at the CO2. Is it acid, base, or normal?
Acid.
It is acid, so that can't be what's caused the pH problem. So let's move down to the bicarbonate, the metabolic component. Is that acid, base, or normal?
Base.
Base.
Base. So we have a metabolic alkalosis. And then the next question is there compensation? So we'll look to the respiratory component for
sir.
compensation.
Yes.
And is it getting the job done?
Yes.
Yes. That's borderline,
is.
but yes.
It's borderline, right on the border, but it's still, yeah, it's still in that 7.45. So we would call this a fully compensated metabolic alkalosis. All right. So I think I've given you examples of all the major deficits, both metabolic and respiratory. So now that we have some examples and we have a working understanding of how to interpret ABGs, I want to talk about some of the things that can cause acid-base imbalances. But first, I just want to spend some more time talking about compensation. So when we see compensation gives us an idea of how far into the process somebody is. So when we see an uncompensated, acid-base imbalance, that generally means that whatever the problem is, it is an acute problem. And does everyone know what acute means?
A sudden onset.
Yeah, it hasn't been going on very long, right? We're not very far into the problem. And then as we develop compensation, both partial and full compensation, this tells us that we are less acute. We are either subacute or we have some sort of chronic acid-base imbalance, because enough time, this has been going on long enough for the body to compensate, right? So for example, let me just tell you that you have a patient that has overdosed on an opioid overdose. So a fentanyl, let's say it's a fentanyl overdose. And I'm going to give you 2 ABGs. One ABG, let me give you another ABG.
So would his first one be respiratory acidosis?
Well, let me put them both up first. All right. So I've got a patient that is overdosed on opioids, fentanyl. And I have 2 ABGs, ABG1 here and ABG2 here. And what I want to ask you all is, which of these ABGs is most consistent with a patient who has overdosed on opioids? So let's go ahead and interpret the ABGs first. So ABG1, pH, acid, base, normal, acid, normal, base, normal. On acid, good. CO2, acid, base, or normal?
It's acid. Acid.
Good. Bicarbonate, acid, base, or normal?
Normal.
It's normal.
Normal. All right. And even though we don't use PaO2 for acid base, we can still look at the PaO2 and we notice that it is low, right? And so we have hypoxemia going on because it's less than 80. All right. So here I have what? I have a respiratory acidosis, and is there any compensation?
Negative.
So I have an uncompensated respiratory acidosis with hypoxemia, low blood oxygen. All right, so that's one ABG. Let's look at this other ABG. So pH, acid, base, normal, acid, normal, base, normal.
It's acid.
It'll still be acid,
It's full on acid. CO2, acid, base, or normal?
acid,
Acid.
Acid. Bicarbonate, acid, base, or normal?
your base.
Base.
Base. And then the CO2 is still low, so this is hypoxemia as well. So here I have a respiratory acidosis. Does everybody agree?
Yes, sir.
And is there compensation?
Partial.
Partial.
Partially compensated.
Yeah,
Yes,
yeah,
there is.
partial.
Just not getting the job done. So this is a partially compensated respiratory acidosis. So here's the question. Which of these ABGs would be most consistent with an opioid overdose? Somebody's overdosed on fentanyl, say.
Number one.
The one.
Why? Why would number one be most consistent with someone who has overdosed on an opioid?
Because it just started, so it's acute.
They ain't breathing as much, basically.
Well,
Sudden thing.
I think because there's no compensation at all.
there you go, right? There's no compensation. So that means this lack of compensation, this uncompensated, means that whatever is causing this respiratory acidosis, it is an acute problem. And opioid overdoses are acute in nature, right? Because if this is a chronic opioid overdose and the patient wasn't breathing, well, they would die eventually, right? So ABG2 would be inconsistent with an acute opioid overdose, right? Does that make sense? Is everybody okay with that specific situation there?
Yes.
Yes.
Okay, great. Okay. So yeah, I just wanted to bring that up, that compensation, the presence or absence of compensation gives us some idea of how far into this process somebody has been, right? All right. So now what I want to do is I want to spend a little bit of time talking about things that can cause these problems. And so what I'm going to do is I'm going to start with respiratory acidosis first. So let's just talk about respiratory acidosis, and hopefully this will be fairly intuitive. It's the metabolic problems that tend to be a little more difficult, but with respiratory acidosis, what's happening is the patient is retaining carbon dioxide. So they are not able to get rid of CO2, or they are making too much CO2. It's typically going to be the latter. Typically, the most common cause of a respiratory acidosis is carbon dioxide retention. So things that inhibit the ability for the respiratory system to get rid of carbon dioxide. All right. So you have, and I'll give you some examples, right? You have CNS depression can cause this. So think of opioid overdoses, right? Benzodiazepine overdoses can do this as well, right? So they decrease the rate and depth of ventilation, right? That's a common one. All right. This can also be due to some neurological problem, right? Damage to the respiratory centers in the brainstem, the pons, the medulla of the brainstem, for example, could do it as well. All right. So that's one common pathology that can cause respiratory acidosis is CNS depression, right? Another common one is lung disease. Specifically what we call obstructive diseases. These are diseases that obstruct the airflow out of the lungs, so you're not able to efficiently move air. So these include things like asthma and COPD, very common for COPD, chronic obstructive pulmonary disease. So things like chronic bronchitis, emphysema, cystic fibrosis, bronchiectasis, right? Sometimes we can see this with certain cardiac diseases as well. For example, severe cases of congestive heart failure, exacerbations might cause respiratory acidosis, right? We can also see this with drowning. We can see this in people that are in cardiac arrest. All right. they're not being ventilated adequately. They can retain CO2. And often what will happen is right before someone in cardiac arrest, if someone in cardiac arrest has ROSC, does anyone know what ROSC is?
Return to spontaneous circulation.
Return of spontaneous circulation. Often what will happen is when you get return of spontaneous circulation and the heart starts beating, all that blood that hasn't really been circulating through the body that's full of carbon dioxide starts going into the lungs, and you will see a massive spike in the CO2. So the end-tidal, for example, the end-tidal CO2 will spike. And if you see a large spike in the end-tidal CO2 during a cardiac arrest, that often means that you have ROSC, right? And now that blood that has all that CO2 in it is beginning to circulate through the lungs. Okay. So these are all problems you want to think about when you see a respiratory acidosis on the ABG. Is this somebody's retaining CO2 or making too much CO2? And there are some fairly rare conditions where people make too much CO2. And you might see this in something called malignant hyperthermia. Has anyone ever heard of that term before? Malignant hyperthermia. Anyone heard of that?
Yes.
What is it? It looks like someone's heard of it. What is it? What do you know about it?
So I've seen it once in the hospital, having to do with post RSI drugs. Sometimes they'll have an allergic reaction to that post RSI drug, and the result of that, they'll become hyperthermic.
So yeah, you're on the right track. Yeah, so it's not an allergic reaction, but it is a reaction. And so what malignant hyperthermia is often a reaction to certain medications, typically medications surrounding airway management, like anesthetic drugs, inhaled anesthetics, occasionally paralytics like choline. And essentially what it is it's a genetic defect that some people have, and we have little receptors, what are called retinine receptors. It is a type of calcium channel in your muscles. And does everyone know how muscles contract?
Movement of
calcium.
in and out of
Yeah.
So
So if we take a big picture look, you've got the muscle here. Let me just draw this. So you got the neuromuscular junction right here, often called the end. Whoa, my notes just crashed. There we go. So you have the neuromuscular junction here, often called the end motor plate. And the way that this works is, right, the action potential moves down the neuron, gets the into the axon, and little vesicles of acetylcholine molecules get released, and that acetylcholine passes a little synapse and attaches to acetylcholine receptors in the on the muscle, specifically nicotinic M receptors, and those little sodium channels. And so when the acetylcholine attaches, it causes the sodium channels to open, and sodium ions rush into the muscle and depolarize the muscle, right? And so you have this depolarization occurring along the surface of the muscle until you get to a little hole in the muscle, and it's like a little tube that goes down further into the muscle. And that's called a T-tubule. And that wave of depolarization works its way into the T-tubule, it depolarizes the T-tubule, and it gets to this little structure deeper in the muscle. And that little structure is called the sarcoplasmic reticulum. And you have a bunch of calcium ions stored in the sarcoplasmic reticulum. And when it gets depolarized, those calcium ions are released. And those calcium ions act on the thick and thin filaments. So in anatomy and physiology, did you all learn about the sliding filament theory of muscle contraction? Was that something you all learned? The sliding filament theory or mechanism? Yeah. So essentially what you have thick and thin filaments. So you've got the actin and the myosin. The myosin's kind of thick and the actin is thin, right? And the actin and myosin are kind of held apart. There's a little site called the tropomyosin binding site that pulls them apart. And when that calcium comes in, it opens up that site, that receptor, and allows the actin and myosin to pull together, right? And that causes contraction of the muscle. And then what you have to do is you have to actually put ATP in to the muscle. So you make ATP. ATP comes in, kicks the calcium off, and reestablishes the tropomyosin binding site, and that pulls the muscle apart and allows the muscle to relax. And then that calcium goes through channels to get pumped back in the sarcoplasmic reticulum, and there are special receptors that pump it back in, and in certain patients that receptor is abnormal, and it takes more ATP than normal. It takes a substantial amount of ATP, so the muscle's cranking out massive amounts of ATP to try to pump that calcium back through those abnormal channels, right? And so what happens is you're making a massive amount of ATP, which means you're releasing a lot of heat, which also means you're making massive amounts of what in the Krebs cycle? What's coming out of the Krebs cycle as a waste?
Lactic acid.
Not lactic acid, but CO2, right? So massive amounts of CO2 are coming out of the Krebs cycle because we're dumping a bunch of pyruvate or acetyl-CoA into the Krebs cycle, right? And we're creating all CO2 waste. So what happens is your temperature spikes up and your carbon dioxide levels spike up very high as well. And it doesn't matter. Oftentimes you can't ventilate these people enough, right? They can't breathe fast enough and deep enough to get rid of the CO2 because they're making so much of it. So that would be a situation where you would have a respiratory acidosis, but it's because the patient's making too much CO2 rather than retaining the CO2 that they're making. But either way, it is an increase of carbon dioxide in your body, right? Because that carbon dioxide that gets converted to carbonic acid, the carbonic acid gives hydrogen ions, and that is what causes the pH to go down while the CO2 is going up. All right. So that's respiratory acidosis. Respiratory alkalosis, on the other hand, is going to be things that cause you to breathe faster and deeper. So respiratory alkalosis are going to include things that are going to increase the rate and increase the depth of breathing, right? So lots of things can do this: pain, anxiety, increased body temperature, right? Certain drugs that activate the sympathetic nervous system, right? Cocaine, amphetamines, those kinds of things. All right. And we can do this as well. Providers can do this. We can do this if we are providing positive pressure inhalation and we are ventilating our patient at a rate that is inappropriate. So we are ventilating the patient at an inappropriately high rate, or we are bagging with too much volume, right? So oftentimes we can do this. This is generally not a good thing to do, as we'll learn here later on. So that's respiratory alkalosis and respiratory acidosis. So now what I want to do is I want to talk about the metabolic problems because they are in some sense a little more complicated. So let's talk about metabolic alkalosis first. All right, so metabolic alkalosis. So this is a bicarb that is elevated. So you have too many bicarbonate ions in your blood or too few hydrogen ions in your blood. So there are two major ways. So we made G and the patient has a metabolic alkalosis, right? These are the things I want you to think about. All right. So first, there are conditions where we lose hydrogen ions. So you have an excessive loss of hydrogen ions. All right. That's the first major category of problems that can cause metabolic alkalosis. The second major category that can cause metabolic alkalosis is a retention. We are retaining too many bicarbonate ions. So we have a retention of bicarbonate. All right, so we're either getting rid of too many hydrogen ions or retaining too much bicarbonate. So let's talk about the loss of hydrogen ions first. There are two areas in the body where we tend to lose hydrogen ions. We can either lose hydrogen ions through the gastrointestinal tract. These are what we call GI losses. All right. And the two common ways that we lose hydrogen ions through the gastrointestinal tract is by vomiting or through gastric suction or gastric drainage. So a gastric tube is placed and we are constantly suctioning this out, right? Why? Why just excessive vomiting or excessive suctioning of the stomach? How can that, can someone explain to me why we're losing hydrogen ions that way?
Because the hydrochloric acid in the stomach is naturally acidic.
Absolutely. Yeah. So if you look in the stomach here, so you have your blood. Imagine this is your blood and you have chloride ions floating around in your blood. And then you've got gastric cells, all right, in your stomach. And your gastric cells are producing carbon dioxide, right? And so the CO2 is combining with water like it does, and it is producing H2CO3, right? It's carbonic acid, and then it breaks down into hydrogen ions. The hydrogen ions get pumped into the stomach, and then the bicarbonate ions go into the blood. And so a negatively charged ion goes into the blood, which allows them to pull a negatively charged ion out. So bicarbonate changes or switches places for chloride, and then hydrogen and chloride ions combine to form HCl in the stomach, right? Hydrochloric acid. And then if you vomit excessively, you start losing all of these hydrogen ions, and you are taking on, right? You have the buildup of these bicarbonate ions, and you're losing the hydrogen ions, right? So that's how excessive vomiting or gastric drainage can lead to a metabolic alkalosis. The next major area where we tend to lose hydrogen ions is through the kidneys. And we call these renal losses. And there are several things you want to think about. Diuretics. Diuretic drugs can do this. People who are on a low sodium diet, all right? So the way the kidneys work, we'll talk about kidneys in a lot more detail later on in the paramedic program, but the way the kidneys work is if you have low sodium, right, that interferes with a hydrogen sodium transport mechanism, essentially, in the tubules of the kidneys. And you end up losing excessive amounts of hydrogen ions because the kidneys are trying to hold on to sodium, because the golden rule of thumb, as you all are going to learn about in fluid and electrolyte balance here in a day, is wherever sodium goes, water follows. So water follows sodium around, right? Sodium is a major solute, and water is a solvent. So diuretics and low sodium diets can cause us to lose lots of hydrogen ions. Hypochloremia. So hypo means low, chlorine means chloride, emia is blood. So this is low chloride concentration in the blood can cause renal loss of hydrogen ions. Hypokalemia. Does anyone know what hypokalemia is?
Low potassium.
Low potassium in the blood. Yeah, so hypo, low, K is potassium, emia is blood. So low potassium levels in the blood. And diuretics, certain classes of diuretics are very good at causing you to pee off potassium, such as the so-called loop diuretics like Lasix or furosemide. And then, excuse me, the last major one is actually hypovolemia. Hypovolemia can cause you, that's low blood volume, can cause you to have a renal loss. We particularly see this in kids. This is fairly common in kids who are dehydrated to have a metabolic alkalosis. All right. So those are the major problems you want to think about when it comes to a metabolic alkalosis, as far as losing hydrogen ions. And there are really only a couple of things that cause us to retain or cause us to create more bicarbonate ions than normal. And they're not particularly common, but I will mention them. The first one is if we are giving somebody bicarbonate, right? So if we are giving them bicarbonate infusions, usually that's in the form of sodium bicarbonate or NaHCO3. So if we are giving an infusion or boluses, right? And sometimes we do this, right? Sometimes sodium bicarbonate is given to patients in large amounts to treat certain conditions like hypokalemia, life-threatening elevation of potassium in the blood, or certain other kinds of poisoning like salicylate toxicity. Sodium bicarbonate is sometimes used, right? So occasionally we would see that, but we would expect an alkalosis. And in many cases, we are trying to cause a metabolic alkalosis when we are giving bicarbonate infusions. And then very rarely, there may be some other alkalotic substances that you can run into. So ingestion of other alkalotic substances. For example, sodium bicarbonate or calcium carbonate. right? You might see this in like Ketones, for example. So certain antacids, somebody is ingesting large amounts of antacids, you might see a metabolic alkalosis there. So that is metabolic alkalosis. All right, so is everybody okay there with some of the major conditions that can cause metabolic alkalosis, respiratory acidosis?
Yeah.
All right, cool. So I think what we're going to do is we're going to look at taking a break, and then the last part of lecture, we're going to talk about metabolic acidosis, and this is the most complex one. And in fact, there is math that we need to do anytime somebody has a metabolic acidosis. There's an additional assessment that we need to do, but we will spend the next hour talking about that in some detail. So let's go ahead and take a break. Let's see, it's about 10:30, so I'll see you all at 10:45. Just a little early, so before we get going, I just want to see how everyone's doing so far. So I know I'm covering a lot of stuff, so since we're just a couple minutes early, how's everyone doing? Is there anything that I need to go back over, or how are you all doing with understanding?
Doing good.
Doing good. Okay. Okay. That's good to hear. I understand this could be a really big jump for some people. So I just want to make sure y'all are feeling okay. All right. Good. So I'll get going here in a couple more minutes. I'm just prepping some stuff for you all. All right. And I'm going to go ahead and share the iPad screen with you all. Again. All right. So now what we're going to do is we're going to talk about metabolic acidosis. And this is one of the more complicated subjects that we're going to talk about in pathophysiology. Well, it's all fairly complicated, but this can be pretty complicated. So let's just build up the foundation for understanding. So when it comes to metabolic acidosis, all right, there are a couple of paradigms for metabolic acidosis. That is, there are two major ways that you can have or you can develop metabolic acidosis. All right. And it has to do with a very special concept, very important concept, critical concept known as the anion gap. All right, the anion gap. So what is the anion gap? What's going on there? Well, the critical point to understand when it comes to the anion gap is the following. There is a chemical idea called electroneutrality. Electroneutrality. And this goes back to last week when we talked about the chemistry of life. And remember that I said in nature, for every positive, there's generally a negative when we talk about the electrical charge. And that is true in the human body. So the positive charges in the human body, for every positive charge, there needs to be a negative charge, all right, to balance that out. Because if you have too much negative or too much positive charge, then you become electrically charged, right? And you can do this by like rubbing your hand on a carpet. And if you pick up extra electrons, you become electrically charged. But as soon as you touch something, what happens? Well, those electrons move away to maintain electroneutrality, and you get that static electrical shock, right? That pop as electroneutrality is maintained. And this happens inside of your body as well. All right. And so I just say that the positive charges, all the positive charges and all the negative charges in your body more or less have to cancel out, right? And so what we do is we can look at the major cations, all right? The major cations in the body and the major anions in the body, all right? And the major cations in the body include sodium and potassium. Those are the two major positively charged. There are many other positively charged ions, but these are the major ones, all right? And the major anions in your body include chloride and bicarbonate. Okay, those are the major anions in your body. And at any given time, the number of positive charges that you have should more or less be equaled out by the number of negative charged particles in your body, or anions. And the difference between cations and anions is what's known as the anion gap. All right, so the anion gap is the difference. So what we do is we take the sum, right? That's sigma, that just means add them all up. The sum of the major cations, and we subtract from that the sum of the major anions. And whatever that number is, that is referred to as the anion gap. And as you might imagine, that number is generally going to be very small. Should not have a very large anion gap, right? So how do we actually calculate the anion gap? Well, what we do is we add the major cations. So you find the sodium and you add the sodium to the potassium. And then you subtract from that the sum of the major anions. So you take the chloride and you add that to the bicarbonate. And then that equals the anion gap. Right? Is everybody okay so far? Now, the anion gap is never zero because, again, there are some anions and cations that we don't directly measure. So there has to be a little wiggle room there, right? Because we don't measure everything. And so a normal anion gap, a normal gap for our purposes is going to be less than or under 16. Is actually kind of a range. It's approximately 12 plus or minus 4. So we just say it in under 16 is what we consider a normal gap for our purposes for today. And that's 16 milliequivalents per liter, because remember, electrolytes typically measure in milliequivalents per liter because they are charged, right? And remember, equivalent is just moles times charge, right? And then 1/1000th of an equivalent is an MEQ, a milliequivalent. All right, just to remind ourselves from chemistry last last week. Okay, so that's what we do. So briefly, let's just talk about what the normal values are for some of these cations and anions, and we're going to cover these in much more detail tomorrow when we talk about begin talking about fluid and electrolyte imbalances. So let's talk about them. So does anyone happen to know what the normal sodium level is?
Normal sodium should be 135 to 145.
Good, good. So 135 to 145 milliequivalents per liter. So let me just write that. So your normal sodium is 135 to 145 milliequivalents per liter. And this is in the blood plasma, right? What about the normal potassium? What's the normal potassium?
3.6 to 5.2.
That's, yeah, pretty close. I generally go with 3.5 to 5 because it kind of rolls off the tongue easy, but 3.5 to 5 milliequivalents per liter is normal potassium. What about normal chloride? Does anyone happen to know what the normal chloride level in the blood is? I just remember 95 to 105. Some people will say 96 to 106. I just kind of go with 95 to 105 because that's a 5. And then, 135, 145, 3.5 to 5, 95 to 105. It just kind of rolls off the tongue. So 95 to 105 milliequivalents per liter is normal chloride. And then let me ask a question. What is the normal bicarbonate?
22 to 26.
There you go. Yeah. 22 to 26. So it's kind of the odd one out, milliequivalents per liter. All right. So in a normal situation, let's just say that somebody has a sodium of 140, a potassium of 4, a chloride of 100, or we'll just make that 105. What the heck? A chloride of 105 and a bicarbonate of 25. All right. Let me make sure you all can see that okay. Go. Okay, good. So what I'm going to do is I'm going to add the sodium and the potassium, and that gives me 144. And then I'm going to add the chloride and the bicarbonate, and that gives me 105 plus 25 is 130. All right. And then I'm going to go 144, and I'm going to take 130 from it. All right. So that gives me 14. So this person would have an anion gap of 14 milliequivalents per liter. All right. So is everybody okay with what the anion gap is and how to calculate it?
Yes. My question would be, when would we get the numbers to calculate it?
You will be given the labs.
Oh, okay.
Yeah, so you got the patient's ABG, and then they have something called the chemistry, their blood chemistry, and we'll be talking about all of those a little later on. But you'll be given this information, or you'll run the lab. If you were working for a service, for example, that has an ISTAT, you may just run this lab, run the ABG. And this is a great segue into the following. Anytime you identify a metabolic acidosis, it doesn't matter if it is an uncompensated metabolic acidosis, a partially compensated, or fully compensated. Anytime we find a metabolic metabolic acidosis, we have to calculate the anion gap. The reason that we have to do that is there are two major forms of metabolic acidosis. There is something that we refer to as an elevated anion gap metabolic acidosis. And there are specific problems that cause an elevated anion gap metabolic acidosis. And then there is something else called a normal anion gap metabolic acidosis, or this is also or often referred to as hyperchloremic metabolic acidosis. That means the same thing. A normal or a non-anion gap metabolic acidosis is the same thing as a hyperchloremic metabolic acidosis. So what is going on here? So everybody's okay with electroneutrality, right? That the positives generally need to equal the negatives, okay? So what I'm going to do here is I've drawn some pictures up here to try to help explain this a little better. So in the middle, excuse me, in the middle, we have a normal situation. We have a normal situation, all right? This is a patient that does not have an acidosis. Their acid-base status is normal, and their electrolytes are normal, all right? So let's go ahead and fill in things a little bit here. All right, so what I want to do is imagine that these are blood. These are little columns of blood, and these are the electrolytes dissolved in the blood. So what is the most common positively charged electrolyte going to be in your blood?
Would you say potassium?
No. Well, what's the potassium level in your blood?
Oh, it would be
Salt.
sodium.
Say it again. Yeah, sodium is the dominant cation in your blood. Potassium is the dominant cation in your cells, the intracellular, but we can't measure inside of the cells correctly. We can only measure the blood plasma specifically. So when we look at the blood, we have got sodium. All right, so on the left-hand side of this, I've got sodium, and let's just say we'll keep it normal here. We'll use this example that I use down here. So let's just say that I have 144 milliequivalents per liter of sodium. All right. And then the next one is going to be potassium down here. And we said that this person had a potassium of 4. Or 140, excuse me. Right? Yeah. There we go. 140. There we go. 140. And then the potassium was 4 milliequivalents per liter. All right. So on the right-hand side, I have to have negatives that add up to all the positives on the left. So let's choose a different color here. So let's choose blue for the chloride. All right, so in this particular patient, I said the chloride was 105, right? And so the chloride is going to be here. Chloride is 105 milliequivalents per liter. And then bicarbonate, and let's make the bicarbonate green. So the CO3. And in that normal patient, we said it was 25 milliequivalents per liter. And then the top right is the anion gap, right? That's the difference, right? So this is the anion gap, right? So this is all the other negatives that we need to balance things out, in essence, is what the anion gap is. And we calculated that as being 14. So the anion gap is 14 milliequivalents per liter. And everything adds up, right? So I've got 144 milliequivalents of positive on the left and 144 milliequivalents of negative on the right. Is everybody okay there?
Yep.
Okay. So now what I'm going to do is I'm going to talk about the types of acidoses. So the first type, and in both instances, what's going to happen is your bicarbonate level is going to decrease. So when I become acidotic, what happens? I have a decrease in the bicarbonate here. Does that make sense? Because I'm either losing it or it's being used up by hydrogen ions. Does that make sense?
Yeah.
So as I'm becoming acidotic, I'm going to be losing these bicarbonate ions, which means to maintain electroneutrality, I need to have some other negatively charged ion to move in to take the place of the bicarbonate that I'm losing, right? If I'm losing a negative, some other negative needs to move in to maintain electroneutrality. All right. And let's talk about how that happens. All right, how that happens. So on the right-hand side here, I have what's known as a non-anion gap metabolic acidosis. All right, so do you see what happened to the bicarbonate here? Can everybody see what happened to the bicarbonate here on the right? What
Yes,
happened
sir.
to the bicarbonate? The bicarbonate shrank, right? I lost bicarbonate. The sodium still the same. The sodium didn't change. The potassium is still the same. It didn't change. The only thing that changed was the bicarbonate. But here's the thing. What increased? What moved in to take the place of that lost bicarbonate?
Your chloride.
All right.
The chloride. You see that here? The chloride, I have an increase in chloride ions. Right? So the chloride ions are increasing. So maybe to make the math simple, maybe the bicarbonate dropped to 20 here, right? And so the chloride increased to 110 here, which means the anion gap is still 14, right? It didn't have to change. And 14 plus 20 plus 110 equals 144. So the anion gap stayed the same. Is everybody okay there? So in non-elevated anion gap metabolic acidosis or hyperchloremic acidosis, chloride ions take the place of the lost bicarbonate. Does that make sense?
Yeah.
Okay. On the other hand, in an anion gap metabolic acidosis, what happens is, remember this is the sodium here, This is the potassium here. This is the chloride. So you are still losing bicarbonate ions. So you all see that the bicarbonate has decreased here, right? Everybody see that? So maybe the bicarbonate is 20 instead of 25, so it's gone down. But instead of chloride moving in to take the place of the lost bicarbonate, what happens is the anion gap increases. So you can see the anion gap has gotten larger there on the left. And so now the anion gap is 19, right? 19 milliequivalents per liter, which is greater than 16, right? So now we have an anion gap metabolic acidosis. Did everybody see that there?
Yes.
Okay. The reason that this anion gap is getting larger is that there is some organic acid. There is an organic acid that is releasing anions. And those anions are taking the place of the lost bicarbonate, right? So there's some organic acid that when it breaks down, what's left over, and we've been talking about this, the anion that's left over stays there and it's negatively charged, so it maintains electroneutrality. So you have unmeasured anions that are increasing. So something is adding mystery anions that we can't directly measure, and that is what's increasing the anion gap. All right. So going back here. So when we talk about a normal anion gap metabolic acidosis, what is literally happening is you are just literally losing hydrogen or bicarbonate ions. So you're having a loss of bicarbonate ions. You're not gaining hydrogen ions, because remember, when I gain hydrogen ions, those hydrogen ions are popping off of something, and whatever that something is, it becomes negatively charged, right? Like lactic acid becomes lactate, right? So I'm losing bicarbonate ions, and there are three areas where we can lose bicarbonate ions. The first is through the gastrointestinal system, GI losses. Unlike metabolic alkalosis, however, we tend to lose base out of our butt. You lose acid out of your mouth and you lose base out of your butt. So I want you to think of diarrhea. Excessive diarrhea tends to cause metabolic acidosis. Fistulas typically that involve the pancreas. And what is a fistula? When I say fistula, what is that? What is a fistula?
Isn't it kind of like an abscess?
Abscesses can actually lead to fistulas or cause fistulas to form. So there can be a relationship. Fistula is a false passage. So there's a false passage that develops. Like if you have a tracheoesophageal fistula, that would be a false passage between the trachea and the esophagus behind it. In this, what happens is you can get a pancreatic fistula, a little passage that connects the pancreas to typically the intestines. And the reason that's important is that's where bicarbonate is made. Lots of bicarbonate is made in your pancreas, and then the pancreas will secrete that into the pancreatic duct with other enzymes, and then that goes into the common bile duct and gets dumped into the small intestine. And that's what neutralizes the stomach acid, right? So bicarbonate from the pancreas neutralizes stomach acid. So if you have a false passage where bicarbonate is just constantly flowing out of the pancreas, you will be losing bicarbonate. Likewise, if you have lots of diarrhea, you're going to lose lots of bicarbonate ions. So you're losing bicarbonate ions, and then chloride ions are shifting in to take the place, right? So the anion gap does not increase. The other major loss is from the kidneys, or we call renal tubular loss. And there's a specific condition. We'll talk about it in more detail later on, not today. I just want you to know the condition for now. And it's something called RTA, or renal tubular acidosis. RTA, and actually like 4 types of it. It's really complicated, but renal tubular, it's dysfunction of the renal tubules that can lead to excessive loss of bicarbonate. And that's what we need to know for today. And then the third one is just an ingestion of something that can cause us to lose bicarbonate. And this is a much more rare. So GI and renal tubular losses are the most common causes of a normal anion gap metabolic acidosis, ingestion, hyperalimentation. So if somebody is receiving like tube feeding, for example, or something called TPN, total parenteral nutrition, where they're getting nutrition through an IV, for example, if they are receiving too much or the wrong kind of formula, that can cause it. And then very rarely, ingestion of ammonium chloride can cause it. But by and large, these are the 2 most common causes. So if somebody has a metabolic acidosis, you calculate the anion gap and it is normal, these are the 2 things you want to be thinking about. Is this patient losing carbonate from their GI tract, or are they losing it from their kidneys? All right. Now, on the other hand, when it comes to an elevated anion gap, so you find a metabolic acidosis, you calculate the anion gap, it's elevated, you want to be thinking what kinds of organic acids are being produced to cause those unmeasured anions, right? All right. And this is almost always due to an accumulation of fixed acids. So fixed acid accumulation. Remember, fixed acids are acids that cannot be eliminated through the respiratory tract. For example, if I have, let's see, let me think of a really common one. Lactic acid. Yeah, right. I'm in a shock state and my body's producing lots of lactic acid, right? So remember, lactic acid looks like this. So that's lactic acid. So when lactic acid dissociates, this hydrogen pops off and you're left with this here. And this is negatively charged, right? This is the anion, and then this pops off as a hydrogen ion. So it is the accumulation of lactate ions, or anions rather, that increases the anion gap. Because I have these lactate anions building up, I don't need negatively charged chloride ions, right? So as you can imagine, lactic acid is one of the causes of elevated anion gap metabolic acidosis. So what I want you to think of is, with your differential diagnoses for an elevated anion gap metabolic acidosis, I want you to think of mud piles. These are the major differentials to think about when there is an elevated anion gap metabolic acidosis. So what does that stand for? That stands for following. I want you to think of metformin and methanol. Metformin and methanol. Methanol is a toxic alcohol. It's sometimes called wood alcohol, and it actually gets converted to organic acids like formic acid. All right. So methanol and metformin, or metformin and methanol. That's the M. U is uremia. Does anybody know what uremia is? You ever heard of that term, uremia?
Or is that blood in the urine?
No.
Is it uric acid in the blood?
That might be a component of it. Uremia literally means urine in the blood, right? So it's an elevation in nitrogenous wastes. So uremia is, think of it as renal failure. If you literally have urine in your blood, that means your kidneys are failing. So uremia is, think of renal failure, right? So metformin, methanol, uremia. The D is diabetic ketoacidosis, right? DKA. P is paraldehyde. This is fairly rare now. It's a preservative that's used in some medications. We rarely run into paraldehyde poisoning, but it's still on the listed differentials. The I includes INH, which is a medication used to treat tuberculosis, and iron. So iron toxicity. All right. The L is lactic acid. We have raised levels of lactic acid. Somebody's in a sustained shock state, for example. All right. E is ethylene glycol. Ethylene glycol is another toxic alcohol like methanol, commonly found in radiator fluids. Okay. And then S are salicylates. All right. Can anyone give me a common example of a salicylate?
Aspirin.
Awesome. Aspirin is one of the most common examples of a salicylate. It's acetyl salicylic acid. And good. There are other salicylates like wintergreen oil, or oil of wintergreen is a very concentrated salicylate. So this is the mud piles mnemonic. So when you, just to conclude, when you identify a metabolic acidosis in your patient, doesn't matter if it's uncompensated, partially compensated, or fully compensated, when you identify a metabolic acidosis, all right, you need to calculate the anion gap. If the anion gap is normal or not elevated, these are the things you want to think about up here, right? What kinds of things are causing my patient to lose bicarbonate ions? If the anion gap is elevated, then you run through mud piles and you go, okay, is there any reason to believe that there's metformin? Does anyone know what metformin is? Super common.
Diabetic drug.
It is. Yeah, it's called glucophage. It's a common drug used to treat type 2 diabetes specifically. Is there any history of methanol ingestion? Is there a history of renal failure? Is this patient in diabetic ketoacidosis? Have they had paraldehyde exposure? Are they on INH? They've overdosed on iron. Is there lactic acidosis going on, right? Are they in shock, for example? Is this a septic patient? They're in septic shock. Ethylene glycol toxicity or salicylate toxicity, right? So those are the differentials you work through. All right. Is everybody okay with that?
Yes.
Okay. I know that's a lot of information. The other thing that I want to mention briefly is with metabolic acidosis, oftentimes with a metabolic acidosis, what is the major compensatory mechanism for a metabolic acidosis? How will the body compensate?
Respiratory.
Won't your respiratory be up?
Yeah. So anytime you see a metabolic acidosis, if a patient is trying to compensate, you tend to see an increased rate and an increased depth of breathing. And this is often why you all learned what is a common manifestation of DKA when someone is in DKA. What do they say? What kind of respiratory pattern do they classically have?
What is that, Kuzma?
Kussmaul's. And what are Kussmaul's respirations?
Rapid deep.
Very deep, rapid respiratory pattern. But here's the thing. You can see this in any type of metabolic acidosis, not just DKA, right? So if somebody has overdosed on methanol, for example, or ethylene glycol, or they have aspirin or salicylate toxicity, you're going to see the same kind of respiratory pattern, a deep, rapid pattern. If they have severe lactic acidosis, one of the big games, particularly someone on metformin, if somebody is taking metformin and they are given IV contrast, right? They have to have some sort of radiological study done, and they receive IV contrast. There's an interaction that occurs that will cause them to develop a profound lactic acidosis, right? You might see Kussmaul's respirations with them as well. So Kussmaul's is not always DKA, right? But it is an indication that the patient is trying to compensate for a profound metabolic acidosis. So metabolic acidosis is fairly complicated, and there's additional assessing that we have to do. All right. So before we wrap things up, are there any questions? Anybody have any questions before we wrap things up for the day?
No.
Okay. So I just want to go through and show you all a couple things on Canvas. So I'm going to get out of here because there are some homework assignments that have opened up. I want to make sure you're all aware of those homework assignments. And most importantly, when they are due. So let me do this, and I will share with you all here very quickly. There we go. All right, let me go in and share this. All right. Okay. Oh, excellent. So if you go under acid, base, and fluid/electrolyte module, you will see that a worksheet and a fluid and electrolyte worksheet assignment have opened up. All right. They are both going to be due on February 14th. That's going to be Monday night. So you'll have a weekend to work through these. I would hold off on working on this until tomorrow because there are I've actually pre-recorded some videos for you all tomorrow that are going to cover fluids and electrolytes in some detail. And so you will want to watch those videos and use that information to fill out the fluid and electrolyte worksheet assignment. But there is the acid base assignment. So the way that this works is the assignment is in one tab, and then you turn the assignment in on another tab. So does everybody see acid base worksheet assignment? Everybody see that?
Yeah.
Yes, sir.
Yes.
That's the assignment. So you will click on that. That will open the assignment. You can download it. All right. So that's the assignment here. All right. So there are 10 ABGs that you need to analyze here. So these are the ABGs. So you'll work through, you'll analyze them, uncompensated respiratory acidosis, or whatever your analysis is. And then what you will do is move this down so I can see it a little better. You will click on turn it in here, and this is where you will turn the assignment in on this tab here. And the reason that these are going to be due on the 14th is I have office hours Monday morning. And so if you're having trouble with interpreting the ABGs, that will give you time to log into the office hours, and I can help you out if you're having issues before you have to turn it in. All right. So are there any questions over the upcoming work? The homework assignments? Anybody have any questions there? The ABG and then the fluid, electrolyte, acid base.
The ABG was the stuff that we covered today. The fluid electrolyte one is the one you want us to wait until we get the information tomorrow. Is that correct?
Yeah, you're gonna get most of the information for that tomorrow. So yeah, I'd wait and just kind of focus on the acid base worksheet, the ABGs.
Got it. Thanks.
Yeah, no problem. All right. Well, I'm going to stop it there. And one more time, are there any questions before I let everyone go?
All good here.
No question.
No? Okay.
Question.
No? Okay. We're good in chat. All right. Well, I'm going to wrap it up here. I'll let you all go. Have a great rest of your day, and we will see you all in the morning.
Thank you, Chris.
Thanks, Chris.
Yeah,
Thanks,
thank you
Chris.
all. Thank you all.
Thanks,
Take
sir.
care. You're welcome. All right, let me get this saved.